Hello and welcome back. Today we will talk about the Johnson-Lindenstrauss lemma that I put down last time, and then try to understand, what are the implications of this lemma and how we can, convince ourselves that something like this is true. Just to remind ourselves, what this lemma was saying in pictures roughly is the following, right? So let's say you have an n-dimensional space where n is typically large, and you have a a set of let's call this d-dimensional space where d is typically large, and let's say you have n points in this d-dimensional space, and what you're trying to do is you are trying to map them using some function f to a low dimensional space. Let's say, let me use a different color. So let's say this is a low dimensional space. Let's say this is Rk, using some map f, such that what we really care about is, if I look at any pair of distances in this original space, let's say distance or distance squared in the original space, let's say there are 2 points x and y, and I look at their pairwise distance, I mean distance between x and y, which is x minus y squared, let's say squared distance. Now I want to compare it with, let's say x gets mapped to this point and y gets mapped to this point. Now I want to compare it with the distance that I get after I do the map, which is f of x minus f of y. Remember, these are also vectors in k dimension, and I want to look at this distance, f of x squared norm of f of x minus f of y, and Johnson's Lindenstrauss says that there is a way to map these n data points from d dimension to k dimension such that the distances are preserved almost approximately, by which I mean that if I measure this distance, it's not going to be too far away from the original distance in this precise sense. That is, this is 1 plus epsilon times x minus y squared. That is, it is at most 1 plus epsilon times x minus y squared, and it is at least 1 minus epsilon times x minus y squared. Right. So this is the JL lemma, and we can already see why this is useful, especially if k is much smaller than d, right. So the lemma specifically says that you can find such a transformation f such that k is, maybe I'll use a stronger color, k is roughly like log n by epsilon squared, order of log n by epsilon squared, right. What does that mean? That means that the dimension to which we map these high d-dimensional points is something like log n by epsilon squared. Now last time we spoke that this is an interesting mapping, because what really matters seems to be not the not the original dimension d, but the number of points that are there in this original dimension, because the dimension of k depends only on n and epsilon squared, where n is the number of points for which we wanted to preserve pairwise distances, and epsilon is the accuracy with which we want to preserve it, right. So the larger the epsilon, the lesser the accuracy in some sense. If epsilon is, let's say, 0.1, then we know that after I do this mapping, the original distances are at most 1.1 times the the map distances are at most 1.1 times the original distances, and at least 0.9 times the original distance, which is a good property to have for the map. Now what we want to do today is, well, this is an interesting lemma. We want to understand what is this map, right. So how do we get such a map, and how can we argue that the map that we are proposing indeed has such interesting properties, right. So that's what we are going to do, and for this we will start understanding this by trying to see where the difficulty arises in the first place when we are trying to come up with such a map, right? So the map that that we are going to look at initially are, you know, simple linear maps, right? Linear transformations, which all of us are aware of. Linear transformations are just, you know, matrix multiplications, right? So that's all linear transformations are. So what kind of a map are we talking about? So let's say you have some vector u, and this vector is in d dimension, and then I apply some map. Let's say I call this r, map is ru, and I know that ru is in k dimension. I want Ru to be in k dimension, which means that R itself must be a matrix which is of dimension k cross t, right? So basically, if the map that we care about is a linear map, then what are we saying is that, you know, it's basically a k cross d matrix which we are looking for, right? So then, you know, any vector that I have in the original space, in the d-dimensional space, I can, you know, multiply this matrix with that vector. I will get a low dimensional, you know, vector in Rk, and hopefully I'm hoping that I'll choose R interestingly such that, you know, what I get preserves distances, right? So that's the first thing that we want to try. So we want to see if there is a linear transformation that helps us achieve this goal, right? So let's be kind of greedy here and ask, you know, for the following to hold, right? So let's say this was the original vector's distance squared, and I take any arbitrary vector here, because, you know, if you have n points, then, you know, if I take any 2 points x and y, and then I measure x minus y, that's also a vector in d dimension. So I can just treat it as any vector for now, and then I'm asking, let's say, the length to be exactly preserved after I apply this transformation R, right? So if I have a vector u, and the length is norm u squared, and then I apply this transformation R, which is basically a matrix in k cross d, and I have ru, and then I want to understand the length squared of ru, basically, right? So now basically then we are asking, is there a transformation which, let's say, makes this equal, right? So which means that we don't lose anything in the length at all, right? So that's, I'm just trying to be greedy here, and I ask, you know, not approximately preserved, but then I want it to be exactly preserved, right? So can we, if so, then we should be getting that, right? So we should not even worry about JL Lemma. We should kind of reduce the dimension and preserve lengths exactly. That's a better thing to do, right? So can this happen is the question. So now, which means that what we really want to happen here is, we want, you know, what if I write this as Ru transpose Ru, which is, you know, a vector transpose itself is its length. So this is just U transpose R transpose Ru, which means that, you know, this is some matrix that is sitting inside, on the left hand side we have just U transpose U. Now I want this to hold for any vector, right? So U is arbitrary. I pick an arbitrary d-dimensional vector, and I want U transpose U to be same as U transpose RU. Now, you know, is this even possible in general? Well, if, let's say, I have, let's for the moment take a simple example. You know, I am in some 2-dimensional space, and then I have a vector, you know, somewhere like this, which is U in R2, and what I am doing is I'm kind of, imagine rotating this vector by, let's say, 90 degrees, and then, you know, I'll get this vector, and this rotation is just a linear operation, right? So now this will be Ru, and the length of a rotation after a rotation does not change, right. So, this basically a 90-degree rotation, clockwise 90-degree rotation, and in this case the length has not changed, right. So, it is a transformation, but the length has not changed, right. So, which means that it feels like you know, it's there may be some matrices that satisfy this property, that is, you know, after I do the linear transformation the lengths are still preserved. But now in this particular example that I showed you, I started with 2 dimension and then I rotated and I am still in 2 dimensions, right. So, a rotation does not do dimensionality reduction, right. So, it does not reduce the dimension, it's leaving, I mean I start with some d dimension, I am still in d dimension, I am just rotating it without affecting the length. That is still possible, but then that is not our point, right. So, we want the lengths to be preserved in the low dimension, right. So, which means that, you know, if I take a closer look at this, I want this guy to be an identity matrix. First of all, let us ask what dimension this R transpose R is in, right. So, R has to map, you know, d dimension to k dimension. So, R itself will be in k cross d. Only then when it operates on a d dimensional vector, I will get a k dimensional vector. So, which means R transpose is d cross k, and R itself is k cross d, which means R transpose R is a d cross d matrix, right. So, now we are imagining d to be very large, k to be very small. So, basically this is, you know, geometrically or at least pictorially, this is like a d cross k times k cross d, right. So, which is like a d is larger than k. So, this is d cross k, you know, this is 1 to d, 1 to k cross k cross d, 1 to k and 1 to d, right. So, this is my R transpose and this is my R, right. So, that I do R transpose R, and then what I get is a d cross d matrix, and I want that to be an identity matrix, right. So, if it is an identity matrix, then I have my property preserved, right. So, we want this to be identity, right. So, we are asking, can this be an identity matrix, right. So, if it is an identity matrix, if I can find an R in k cross d such that R transpose R is an identity matrix in d cross d, then I can use that R and then, you know, map any vector u from d dimension to k dimension and still preserve the length. We know it is possible when d equals k, when any rotation matrix will have the property, orthogonal matrix will have the property R transpose R equals I, right. So, that is the definition of orthonormal matrices. But here, you know, this is not, you know, R is not square, right. So, and then we are asking, is this still possible, right. So, we want this guy, so on the right hand side to be an identity matrix, right. So, we want this to be identity. Now, let us look at this, right. So, what should happen for this to be identity? Now, this, let us call this A1, A2, the rows of R transpose as A1 to AD, which are the same as the columns of R transpose AD. Now, what we are saying is that if I take a dot product between A1 and A1 or A2 and A2 with any of these rows with itself, I should get 1, and if I take a dot product with any AI and AJ where I is not equals j, I should get 0, right. So, which means they should be perpendicular. In other words, what we are saying is that if this is true, then we want, you know, A1, A2 till AD to be a set of orthonormal vectors, that is the set of vectors such that they are pairwise orthogonal and the length of the vectors is just 1. Now, here is a question for all of you, is this even possible? Remember, each of these A's are k dimensional vectors, right. So, this row is a k dimensional row, right. So, that is a k dimensional vector, right. So, each of this is in k dimension and we are assuming k is much smaller than d. Now, can I have d orthonormal, set of d orthonormal vectors in k dimension when k is less than d? Well, a basic fact from linear algebra would say that this is not possible. If I have, you know, if I am in k dimension, then I can only find at most k orthonormal vectors, right. So, that would become a basis for Rk, but then I am asking here for, if this is true, then I am asking for more, right. So, what I am asking for is d orthonormal vectors, which is not possible, right. So, this is simply not possible. In other words, what we are concluding now is that, if I just hope that there is some R which is just a matrix which will take d-dimensional vectors, map it to low dimensional k such that the lengths are exactly preserved for all vectors, then there is no such hope, right. So, we do not have hope for such a matrix at all, right. So, which means that the problem becomes harder now. So, our straightforward way of thinking about finding a matrix is not going to work. Now, what JL Lemma says is that, well, first of all, what we have disproved now is the existence of what is called as isometry. Isometry means that you have a map such that it leaves the distances intact exactly, right. But JL Lemma is not guaranteeing you that. It's kind of telling you that there may be a map, right. So, you will not get a map that is going to give you isometry, but you may get a map that will give you an approximate isometry. JL Lemma has this accuracy parameter, remember epsilon, and then all we are saying is that there is a map that will give us an approximate isometry. Now, so that is one relaxation from the stringent condition that we had earlier of isometry. JL Lemma is only guaranteeing approximate isometry. The second thing that JL Lemma is also guaranteeing is, well, I am not going to say that this is going to work for the entire d-dimensional space. I only care about the n vectors that are given to me. Well, these n vectors can be any vectors. I do not have a control over what these n vectors are, but I want to only care about n vectors and their pairwise distances, which means that I only have to preserve n square pairwise distances, right. So, there are only order of n squared pairs if there are n vectors, and I only have to preserve these distances, right. So, if you remember, so this is one distance, this is one distance, this is one distance, this is one distance, and so on. So, there are n squared, n choose 2 pairs, and so n choose 2 distances that I need to preserve, right. So, that is all I need to preserve. I do not have to preserve for the entire d-dimensional space, right. So, these are two extra relaxations that we potentially have, which is at least giving us the hope that maybe something like a JL Lemma could be even true. But what this is kind of telling us, this argument is telling us is that, well, it is going to be very hard to find such matrices, especially if we go take the deterministic route, right. So, that is, if you want to give a deterministic matrix that is going to give us even approximate isometry for any set of n vectors in d dimension, then that is going to be terribly hard to find. On the other hand, what we are going to do is to use the power of randomization to come up with a matrix R, right. So, what we are going to say is that, well, I am going to not worry about isometry, which is very hard to get, which is in fact impossible to get. What I am going to go after is, I am going to come up with a randomized matrix and use the power of probability and randomization to argue that this randomized matrix, when applied to any set of vectors, is going to preserve pairwise distances with very high probability. That is the basic idea that we are going to, or route that we are going to take, right. So, and we will break it down as we go along, right. So, it's going to take some time, but then the wait will be worth it, right. So, let's try and do that right now.